Can you see my PowerPoint slides? On chapter 6 now?
Yes.
All right. I'm going to start from there. We're going to have a test on November 3rd. After we finish chapter 6, we're going to go over questions and answers. Then we're going to have the test. Now the chapter 6 is on alternative energy sources. Now we talked about in chapter 5, fossil fuels, combustion and reactions using fossil fuels. So we need to replace fossil fuels. What are the alternatives we have? We're going to talk about nuclear energy, also solar energy, other alternative biofuels, geothermal energy, biomass, etc. in this chapter. So here, these are the topics. We're going to start with nuclear energy, and then move on to other sources of alternative energy. Now, since 1960s, after we created atomic bomb, mainly through splitting atomic nuclei, we obtain large amount of energy. We're going to look into the ways that we can harness nuclear energy to produce electricity and nuclear energy for peaceful purposes. Now, nuclear energy is based on radioactivity of certain isotopes. Isotopes of elements with atomic number greater than 84 are unstable. Those isotopes are unstable. They decay, emitting three kinds of radiation: alpha, beta, gamma. We're going to talk about it. The decaying of unstable radioisotopes emitting this radiation is called radioactivity. Now, radioactive isotopes have certain half-life. Depending on the half-life, these radioactive isotopes going to be around for a long time. Some of them will be here for almost million years. Some of them will be here for about 1,000 years. Some of them will be around 100 years, depending on half-life of the radioactive isotopes. We're going to look into that, how long they will remain radioactive. Now, when we harness nuclear power, there are risks involved. One of the risks is when you do fission reaction, splitting of atomic nuclei, they're going to produce new radioactive isotopes. Therefore, nuclear power produce various kinds of radioisotopes, which are going to be here for a long time. So storing radioactive isotope is a problem. They can be released to water supply or atmosphere and can contaminate soil and waters. So we have to be careful with them, how we store them. So one risk associated with nuclear power is release of radioactive isotopes through accidents, through when we store them, they can be released. Now we're going to look into future of nuclear power. There is a history of nuclear power plant malfunctions that we are worried about future of nuclear power. We're going to discuss that in this chapter. We're also going to look into solar power to produce electricity. It's direct harnessing of sun's energy through a solar panel, which consists of solar cells. This is non-polluting. There's no emission of carbon dioxide in here. Even the nuclear power doesn't emit carbon dioxide. Therefore, it's carbon neutral. But there's a problem with solar power. To produce solar panels, you have to purify silica. Solar panels are based on silicon chips. Processing sand to produce silicon consume energy. So there will be some problems with that. We're going to look into the origin of solar power using silicon chips, which are crystalline. Now, there are other energy sources apart from nuclear energy and solar energy. There's hydropower, geothermal power, biomass, and even tidal waves could be used, wind power. We're going to talk about them. Let's start describing these alternative sources of energy. Now we talked about energy consumption of the world is 10 to the 3 joules in a typical year. The large amount of energy is used in our human activities, transportation, electricity, and various other things that we do consume a lot of energy. Now, one of the ways to produce energy is through radioactivity. Radioactivity is based on radioactive elements. So we can use them in nuclear power plants to produce electricity. So we have to know how we produce electricity in nuclear power plant and how we keep our environment safe from nuclear waste. There are some environmental effects producing nuclear electricity from nuclear power plants. So fossil fuel power plants mainly cause a lot of carbon dioxide to be released and other pollutant to release. So we have to compare environmental implication of fossil fuel and nuclear energy. The solar energy is energy coming from sun. We talked about UV light and infrared heat energy that is coming from sun. Some of the energy from the sun, light energy, visible region, could be converted to electricity using solar panels. Some of the energy could be used to heat water. There are hot water producing devices attached to rooftops that can heat our homes, hot water, save electricity, and reduce fossil fuel burning coal, and therefore save our environment. So we're going to look into various types of other energy sources. Geothermal energy, hydrothermal energy, hydropower, hydroelectricity, tidal waves, etc. Wind power, as shown in this diagram. Wind power is also used to produce electricity. The energy comes from mainly fossil fuel. We need to go to this website, US Energy Information and Administration website, that publish energy production and consumption for each state. There are various ways that we produce energy. We are going to look into that website in a minute. I'm going to choose Louisiana on that website. And we can look into each state and various sources of energy that each state consumes. What type of energy sources are used to produce energy in each state? How the energy sources differ among different states. Now we're going to pick up another state and compare Louisiana to that state. I would pick up California. So we're going to look into this page and find what are energy, how much energy is produced from fossil fuel, and also energy sources alternative using alternative fuels. On that web page, per capita consumption of energy in 2018, Louisiana consumed 945 per capita. California consumes 202. So we consume more energy because we have energy industry here, oil and gas. We transport a lot of crude oil to other states. So if you look at the details of states, it's given under fossil fuels, nuclear energy, renewable energy. The energy consumption is given in trillion BTU, British Thermal Units, trillion. If you look at Louisiana, coal is used only 20.4 BTUs. Natural gas is a lot, many BTUs produced from natural gas. These are all fossil fuels. Crude oil, we extract. We have offshore and crude oil production platform. We produce 278.7 BTU from fossil fuel, crude oil. Nuclear, we also have nuclear energy, 179.3. I think we have 2 or 3 nuclear power plants. We don't use any biofuels. Biofuels are mainly ethanol and biodiesel. We also burn a lot of wood and waste. And others, 14.8, it's about others means solar and other forms of energy. Total is 3,536 BTUs per year. If you look at the other states, Kentucky uses a lot of coal. I think they have a lot of coal. They don't have nuclear power. Less natural gas, less crude oil. So they have more solar power than Louisiana. If you compare to California, Louisiana and California, California doesn't use coal. It uses natural gas. California uses a lot of crude oil, nuclear and more nuclear power, more biofuels, more wood and other biomass. California uses a lot of solar power, 857 other under solar power. The total energy produced from these energy sources is 2,480.2. We produce a lot of crude oil and natural gas. and we are selling them to other places. Therefore, we make a living out of crude oil and natural gas. So you can see how diversified energy consumption in different states, depending on their natural resources. If you look at energy, total energy, 79.5 come from fossil fuels, coal, natural gas, and crude oil, petroleum. Nuclear power is about 2.2% of the total. The renewables are about 18%. So we have to develop a lot of renewable energies if we have to replace fossil fuels, which is almost 80% of our energy consumption. So that's a huge task. Renewables are broken down into traditional and modern. Traditional is biomass, trees, wood, and other plant material. Modern renewables are broken down into several items. Hydropower, 3.7. Biomass, geothermal, solar heat, solar panels and solar heating. There are a lot of geothermal power trapped inside the earth in the forms of heated water, geysers. We could harness those hot water and use that to heat the homes and produce electricity. Hydropower is produced by natural cycle of water. Rain collected on a reservoir with high potential energy. You can run turbines and produce hydropower. These are environmental friendly. We also have wind, solar, biomass. Apart from solar heat, we can produce electricity. Geothermal power and biofuels. These are the alternative energy sources that we going to look into in detail later in the chapter. The electricity is produced mainly from petroleum and other liquids. Oil and the natural gas is also, and the coal also used for producing electricity. Now, as you can see from top three sources, natural gas is taking over coal now. We are using more natural gas. Coal is significant portion of, still significant portion of our electricity produced from coal. The last two at the bottom are nuclear energy at the bottom, and the other one is renewable energies. that we talked about, solar and other forms of renewables, they are increasing. So we need to increase renewables and totally get rid of first three. How we going to do is a challenge. By year 2040, we have to increase renewable sources almost 50%. That's a huge task. So we're going to look into how we do that and what are the environmental consequences. Now we're going to look into solar nuclear energy, one of the alternative sources to fossil fuel. Nuclear energy is derived from nuclear fission. Nuclear fission is breaking up of large nuclei into smaller ones, and during that process, energy is released. Fission is a breaking up. Why they produce large amount of energy? Now, unlike chemical reactions, nuclear reactions do not obey law of conservation of mass. When nuclei are changed to different nuclei in nuclear reactions, that means elements change from another element to a new element, old element nuclei to new nuclei. There's a mass change during that process. The fission mass of the fission products are slightly less than the mass of the reactant, fission reactant. Therefore, there's a mass defect. That missing mass, about 0.1% of original mass, is converted to energy in various forms, heat, radiation. The energy released by mass defect in chemical fission reaction and nuclear reaction is calculated using Einstein's equation. E is equal to mc squared. To calculate energy in joules, we need mass defect, the missing mass or mass defect, in kilograms, and velocity of light in meters per second, 2.99 10 to the 8. If you know the missing mass or mass defect in kilograms, we get the energy in joules. If you look at that equation, there's a lot of energy released due to destruction of mass during nuclear reactions. So first, we came up with nuclear bomb. Famous nuclear bomb, pictures with the mushroom cloud, is seen in 1960s. First seen in 1960s. The release of energy is based on E, energy is equal to delta M is mass defect C squared. For fission of 1 kilogram of uranium-235, which we use in the nuclear bomb for the first time. The product mass is 0.1 less than the original mass of uranium-235 used. There are other nuclei with lower mass is produced. Therefore, mass defect, if you use 1 kilogram of uranium-235, is 1 times 10 to the negative 3 kilograms. That's the mass defect, 1% of 1 kilogram. So that converted to energy through Einstein equation. Plugging in kilogram of mass defect, velocity of light squared. So you get energy of 9.0, 10 to the 13 joules. A joule is 1 kilogram mass and velocity in meters per second. So if you have 1 kilogram by 1 meters per second squared, meter squared, second inverse squared is 1 joule. Joule is unit of energy. We can convert that to calories. Now this amount of energy is equivalent to 22,000 tons of TNT. Before nuclear energy came, the bombs are made out of explosive using TNT. Therefore, we compare this to TNT. We have to burn 222,000 tons of TNT to get this amount of energy. It's just mass defect of 1 times 10 to the negative 3 kilograms produced. That equivalent to burning 22,000 tons of TNT. It is possible to obtain tremendous amount of energy from very small amount of matter, whether in a nuclear weapon or power plant. So there's a useful energy source. Therefore, nuclear energy is one of the useful source. Let's talk about TNT briefly. TNT is benzene with methyl group and is called trinitrotoluene. Toluene is benzene with CH3 group. It's called toluene. Tri means 3 nitro groups. Alfred Nobel discovered TNT. He became a very rich man, and he also created the Nobel Prize Foundation. So we use TNT to compare explosiveness of explosive power nuclear weapons, as we described in the previous slide. How does TNT work as an explosive? When TNT explodes, 3 moles of nitrogen, 7 moles of carbon monoxide, 5 moles of water is produced from 1 molecule of TNT. Therefore, enormous number of particles are produced. Sorry about that. So TNT, anything that breaks up into large number of particles in a closed space, an exothermic reaction will produce a bomb. So that's how TNT works. Now let's talk about radioactive isotopes of radioactive nuclei. Isotope is a atomic particle with certain number of neutrons and protons. Uranium-238 is one of the isotopes of uranium. Uranium-238. 238 means mass number. If you look in the periodic table, uranium is 92. I'm checking. Yes, atomic number. So 92 is atomic number. 238 is mass number. Mass number is number of neutrons plus protons. So how many neutrons uranium-238 has? 238 minus 92, 146. 146 neutrons, 92 protons, 92 electrons. That's how you calculate. We've done that before. How you calculate the number of neutrons, protons, and electrons from isotopic symbol. All atoms of the element same. How can you distinguish among isotopes? They have different number of protons. Let's check whether we can use what we learned in the previous slide. For the isotopes with unknown element X, mass number 119, atomic number 50. If you ask what is the element, how do you get the what element is this? Element is decided by atomic number 50. So you look up in the periodic table where atomic number is 50. I'm looking, it is atomic number 50 is tin, SN. Therefore, you can answer that question. Atomic number is 50 is tin. Therefore, this should be 119, 50, and X is equal to Sn. How many protons, neutrons, electrons are in carbon-12 isotope? Carbon has atomic number 6 always. But carbon can have carbon-13, carbon-14. We are asking how many protons, neutrons, and electrons are in carbon-12 isotope. Protons are 6. How do I know protons are 6? Atomic number is 6. 12 is the mass number. Therefore, 12 minus 6 is number of neutrons. A neutral atom has same number of protons and electrons. Therefore, 6 electrons in the isotope. How many protons, neutrons, electrons are in chlorine 35 isotope? Chlorine 35 is different isotope. There are some chlorine 36 also there. But the atomic number is same for all the isotopes of an element. So in this case, how many protons? 17 protons. 35 minus 17 is 18 neutrons. Same number of electrons as protons. Electrons are 17. You can do this type of calculations if you're given some problems. Now we're going to look into nuclear reactions. We talked about chemical reaction. We're going to see how the nuclear reactions are balanced. And now we show nuclear reactions using nuclear reactions, like chemical equation for nuclear reactions. For example, uranium-236 capture neutrons. 235 here. I'm sorry, 235, not 236. The first particle here with symbol N is a neutron. Neutron has mass number 1. Neutron don't have atomic number. Neutron don't have charge. Charge of a particle is the atomic number. Uranium-235 has 92 protons and total of 235 protons and neutrons. When it captures neutron particle, it goes to 236. Now one more neutron is in the nucleus, unstable nucleus. Therefore, it breaks up into barium-141. That's a fission reaction. And krypton, 92. And 3 more neutrons are produced. This extra neutrons produced in a nuclear reaction causes these neutrons to initiate another cycle of nuclear reaction and make a chain reaction. We're going to show that chain reaction in a few slides later. How we balance this equation? How we know that there need to be 3 neutrons on the product side? Unlike chemical reactions, we have to balance mass number on the products and reactant side, also the atomic number on the products side and reactant side. For nucleation, superscripts are mass number, subscripts are atomic number. They need to be balanced for reactant nuclei and the product nuclei. If you look at this, uranium-235 capturing 1 neutron. Mass number is 1 for neutron, 235 for uranium-235, and added up to 236 mass number. When you look at the product nuclei, 114 plus 92 plus 3 times 1 is 3, it adds up to 236. If we didn't write down 3, in the neutron in front of the stoichiometric coefficient in the nuclear reaction, it won't be balanced. Now both sides have same mass number. Atomic number of neutron is 0. Uranium-235 is 92. Then we add up barium-141, 56, plus krypton-92, 36, plus 3 times 0. Atomic number of neutron is 0. That adds up to 92. That's how we check if a nuclear reaction is balanced. So you need to do some problems identifying whether nuclear reaction is balanced or not. This is a fission reaction. Fission is breaking up of large nuclei into smaller pieces. Fusion is coming together small atom nuclei to produce bigger nuclei. In the sun, hydrogen fuse, hydrogen react together to produce helium. That's small particles going to producing large particle. It also creates mass defect. Therefore, fusion is another type of nuclear reaction that can be used to produce a lot of energy. How it creates a chain reaction in the reaction we shown in the previous slide. Nuclear fission is breaking up. It's initiated by neutron, one neutron. For each neutron used, 3 is produced. Therefore, net gain of 2 neutrons. So if you look at this, when one uranium-235 undergo fission, it produced 2 more, initiating reaction with 2 more uranium-235. It goes on a chain. So enormous amount of, suddenly all the uranium-235 undergo reactions with neutrons, with excess neutron produced initially. Each of the generated neutrons can initiate the fission of uranium-235, which will generate another 3 neutrons and so on. To this happen, to initiate a nuclear chain reaction, uranium-235 has to be concentrated into 15 kilogram or 33 pounds. Now, we hear about this. Some countries are trying to increase the purity of 235 to create weapon-grade uranium using nuclear waste, like Iran. So 15 kilograms of uranium-235 is not easy to make. There are several ways to make it. Centrifuges and stuff like that are used. In a nuclear bomb, to initiate the nuclear reaction, we use a conventional bomb like explosive, TNT, to push uranium-235 together so that subcritical piece of uranium is produced. This is called gun type assembly method. So that will initiate you can trigger nuclear reaction by secondary chemical explosive that will initiate the critical mass and chain reaction in uranium-235. Anyway, we are more more interested in peaceful uses of nuclear power. When you look at nuclear power plant, there's a huge dome as shown in this picture. Dome is where that control nuclear reaction is maintained at a steady state as opposed to nuclear explosion. In a nuclear reaction, chain reaction occurs in a split second, but that is a bomb. But we don't want that. We want to control the nuclear reaction, release energy in controlled manner. So we use uranium-235 fuel sources in nuclear power plant called pellets. It's about one pellet is uranium oxide pellets, about a dime, size of a dime is shown in the picture. Uranium is extracted and uranium-235, which is uranium oxide, uranium-4 oxide. Uranium has several charge, variable charge. So we use uranium oxide, 4 oxide to produce pellets. And these pellets are put in a nuclear fuel rod shown on the bottom. End to end, composed of zirconium and other metal. Tubes of zirconium and other metal, which are grouped into with steel to a bundle on the circular bundle, the square-like bundle in the picture. So these fuel rods are lowered into nuclear core, where neutron source is there. As you lower the fuel rods into the core with neutrons, nuclear reaction gets started. As we produce more energy, we can pull out the nuclear rods and control the nuclear reaction. So nuclear power plants are used to produce electricity, just like coal burning power plants. Let's compare these two, nuclear power plant and the fossil fuel power plant. There are a lot of similarities. Only difference is the way we heat the steam to produce, the way we produce steam. In the bottom, we look into this nuclear power from fossil fuel, and not the nuclear power, electricity from the nuclear fossil fuel burning. In the nuclear reactor, you use that dome shown in the picture, where the core of nuclear reaction take place. In coal burning, fossil fuel burning power plants, there's only one cycle of coolant water. One cycle of coolant water. In the nuclear power plant, the nuclear core is cooled with another circle of cooling water that's in orange. So primary coolant, which is in blue, is exchanging heat from the nuclear core and the secondary coolant cycle in orange. This is to avoid contamination of water, coolant water, that is sent to cooling towers and ponds. So we have to be careful not exposing materials in the core into the environment. So that's the only difference. The fossil fuel power plant use chemical energy of fossil carbon-hydrogen bonds, breaking and making, while producing carbon dioxide and water. In nuclear power plant, uranium-235 undergo fission reaction, produce a lot of energy, and controlled by controlling rods. So electricity generation is similar. Potential energy of fossil fuels, chemical energy is the potential energy here. In nuclear reaction, potential energy of the neutrons, protons, energy of the nuclei, produce heat and produce steam. Kinetic energy of the steam turn turbine. Turbines turns motor, generator, mechanical energy. Generator creates electrical energy. So they are very similar except the initial step. Electricity generated by nuclear and fossil fuel is identical. Potential energy is converted to kinetic energy when a fuel is combusted. The kinetic energy turns the turbine, which corresponds to mechanical energy. Electrical energy is produced via electrical generator. We talked about that in the previous chapter also. The rate of energy production, power, is joules per second, is called watt. Power is measured in watt. You probably heard about watts, kilowatts, hours. That's how we pay our electrical bills, kilowatt hours. Single nuclear reactor has maximum power capacity between 500 and 1300 megawatts, compared to 600 megawatts typical for coal-fired power plants. Therefore, large amount of heat electricity is produced, power is produced by nuclear power plants. Megawatts is 10 to the 6 watts. Now let's look at the fission reaction and radioactivity, little more detail. Discovered by Marie Curie in 1899, radioactivity is breaking up of atomic nuclei with atomic number greater than 84 to other small nuclei by emission of radiation by certain elements with atomic number greater than 84. Marie Curie won 2 Nobel Prizes, one in chemistry and one in physics. The type of nuclear radiation emitted during the radioactivity is alpha, which are helium atoms, beta, which are electrons, fast-moving electrons, gamma is electromagnetic radiation with high energy. So when a radioactive nuclei decay by alpha emission, its mass number is decreased by 4 and atomic number is increased by 2. When a beta emission occurs from a radioactive nuclei, mass number doesn't change, but atomic number is increased by 1. Beta is considered, emission is considered as neutron. Is converted to electron and proton. Therefore, atomic number is increased by 1. Gamma radiation is just the energy that is released in the conversion of destruction of mass in the chemical reaction, delta M, mass defect. Radioactivity include these 3 radiation, alpha, beta, gamma. So radioactivity alpha is summarized in the table here. Alpha is helium or alpha. Charge is 2+. Same information as in the last slide is in the table form. Gamma is called photon. Photon is light energy. No change in either mass or mass number or atomic number. It's just the energy released during the destruction of mass into energy that large energies release as gamma radiation. Gamma rays are part of electromagnetic spectrum with more energy than X-rays. What is radiation? Radiation is alpha, beta, gamma. So mainly when we are talking about energy changes, you can identify whether somebody is talking about just the electromagnetic radiation or nuclear energy. For example, name a type of radiation that has shorter wavelength than visible light. That we are talking about is electromagnetic radiation. We are not talking about any nuclear reaction. Shorter wave than visible light, that's gamma. We are not talking about nuclear reaction. Gamma radiation from cobalt-60 can destroy a tumor. Cobalt-60 is the radioactive isotope. Therefore, it's a gamma radiation from nuclear reaction, nuclear decay of cobalt-60. That's used by dentists to produce X-rays also. Watch out for UV rays. If you have a pigmented skin, this radiation may cause a sunburn. We are just talking about UV radiation, but UV radiation is produced by the sun by fusion reaction. Therefore, it's a nuclear reaction. UV is a EMR, electromagnetic radiation, that comes from fusion of helium to hydrogen to helium in the stars or sun. Rutherford detected the radiation emitted by uranium. That is a nuclear reaction. So you can understand, sometimes we talk about electromagnetic radiation, sometimes electromagnetic radiation is emitted by nuclear reactions. Neutron generation. One way to generate neutron is to use plutonium and beryllium-9 and alpha particles. So this is one way to initially generate neutrons for nuclear reaction, fission of uranium-235. So plutonium decay to uranium-235 and emitting alpha particle. You can use this alpha particle to react with beryllium-9. Beryllium-9 is given in the second nuclear reaction. Beryllium-9 is converted to carbon-12, gamma radiation, and neutron. So this neutron produced this way could be used in a nuclear reactor. When you lower down nuclear fuel rods, they can initiate the nuclear reaction. The radioactive decay takes place when the nuclei has more than 84 protons, atomic number greater than 84. Uranium-238 decays to thorium, emitting alpha particle. This decay is called alpha emission. That's how the radiation, alpha radiation, can come from. Thorium-234 undergoes beta emission. That means it emits beta emission and get converted to palladium-234. So these nuclear reactions are balanced. If you can see the mass numbers are balanced and the atomic numbers are balanced. That's a helium emission, alpha emission, beta emission. So there's another one called neutron can change into proton. Proton is atomic number 1 and mass number 1, emitting electron. This is a beta emission. That's why we call when a alpha particle, beta particles emitted by a nuclei, it change one neutron to a proton. Therefore, atomic number is increased. Thorium 235 goes to Pa 234. Loss of electron by neutron during the formation of proton. Now, these radiations could be identified in a chamber called cloud chamber. Cloud chamber is a chamber with steam. I'm looking at the time. What time you have? 2:42. We started at 1:30. 2:30. I'm going to stop the class for today. Then we're going to continue and finish the chapter next week. Okay?